So for those of you for whom this webinar may look familiar, this is a repeat performance of a webinar that I gave sometime in April at the beginning of the year. So I apologize if I have not come up with new material, but you gotta get mileage out of these things. And with no further ado, I'm going to get started. So the title of today's webinar is Dr. Strange-Frost, or How to Learn to Stop Worrying and Love Flotation Chemistry. And I might even stop slurring and speak straight as we go along. We're going to start with a bit of an introduction, and we're mainly going to talk about the topic of mineral flotation. All of you should already be very familiar with this, but I'm going to go over it just in case. So, flotation is defined as a physico-chemical process to separate valuable minerals from gangue. It is one of the primary stages of mineral beneficiation, and it is an incredibly complex process. And after working in this area for well over 100 years, it is still not something that we fully understand and have a really good grasp of. So what are the basic principles of flotation chemistry? Flotation chemistry. Please mute your microphones. Thank you. So the basic principles are 3 probabilities of flotation. We have the probability of particle-particle contact, the probability of particle-bubble attachment, and the probability of particle-bubble detachment. To put it in simple terms, in a flotation system, so you have particles and you have bubbles. First, they have to collide. Once they collide, they have to stick. And once they stick, they have to stay stuck. Sometimes the probability term for particle-bubble detachment is expressed as 1 minus P or 1 over P to indicate that it is in fact an inverse probability, but it's simply a question of notation, and depending on which literature sources you look at, they may be quoted differently. That's really nothing to worry about. So when it comes to, in particular, flotation chemistry, the one probability that we worry about the most is that of particle bubble attachment, because it is the one probability that is most influenced by flotation chemistry. That is not to say that the other 2 are not impacted by it at all. That is not at all the case. The probability of bubble particle collision is in fact strongly influenced by Frother properties, because it controls the size and hence the number of bubbles that can be generated given a certain air flow rate. At the same time, the probability of bubble particle detachment is a strong function of the strength of the bubble particle bond, and is therefore a strong function of flotation chemistry. But for the purposes of today's seminar, we are going to be more or less focusing on the probability of bubble particle attachment. And so what happens within a flotation cell, what you have is series of particles which can be subdivided into desired and undesired particles, also known as gangue, as well as air bubbles. We are trying to fix our hydrodynamic conditions in such a way that we have the maximum number of collisions between bubbles and particles, and that the particles we want to recover stick to air bubbles, become recovered into the flotation froth phase, and are then recovered over the lip of the flotation concentrate. Again, this is something that is very, very old hat and familiar to all of you. So let's talk about bubble particle attachment. It is primarily, although not entirely, a chemistry-driven phenomenon. And that chemistry can be adjusted to either encourage the formation of a bond between a bubble and a particle, also to regulate the strength of that bond, but also, if necessary, prevent the formation of that bond in case you do not want something to float, if something is a gangue. So that is a difference between a collector and a depressant. And so all of these control levers can be achieved through a very carefully calibrated suite of reagents, which you add to your flotation system. And so What are the typical flotation reagents that we hear about in mineral processing operations? Well, there are three main types, although there are plenty more. One is the collector, if you want to make something float. The second is a depressant, if you want to stop something from floating. And finally, a frother, which you use to manipulate your bubbles to make them suitable for flotation, but also to control the nature of the froth phase within the flotation cell. There are a number of other reagents that we are normally dealing with, and these are promoters, activators, surface modifiers, flocculants, dispersants, etc. There are quite a few others that I haven't listed that you are likely to encounter as part of a normal operational flotation plant. So how do mineral processing operations approach selection of reagents for their plants? Well, I have listed a number of mechanisms that I am the most familiar with, and the first and foremost among those is that of legacy. Plants will always use a reagent suite that has always been used on that plant. It is a matter of working with what you're familiar with. It is a devil that you know, and if it was good enough for your grandpappy, it's good enough for you. If, however, a plant is relatively new and you need to define a new reagent suite for it, a very common go-to mechanism is to look at what similar operations are doing and copy what has been done. So you find a plant that treats an ore that is relatively similar to yours, or at least treats the same commodity, and make use of the same or a similar reagent suite. So this is also a very common approach. Number 3 is my absolute favorite, and that is site lore. And every site that I've ever been to has their own special piece of lore that has been passed down through the generations of metallurgists. It is a very specialized piece of knowledge. It tells you there's only this particular reagent that will do the job in this particular cell, or for this particular ore, or this particular bank of cells. And if you ask people, how did that idea come about? Why does it work? Nobody can tell you. It is simply information that has always been there and has been passed around. The kicker is that it's often not wrong, but nobody can tell you why it's right. So the fourth option for choosing reagent suites is recommendations from your reagent suppliers, where you call up somebody from your nearest reagent supplier, be they SciTech or BASF or any suite of them that are out there, and they will make recommendations for the kind of reagent that you can test on your operation. Because according to their expertise, this is what will work in your system. What you often don't see is a systematic process of reagent selection that is based on an underlying in-depth understanding of what your ore is in your plant and what the reagents that you are choosing will do in combination with that ore. That is something that can happen very effectively, and I have seen it happen, but those cases are in a minority. Well, why is that? Well, this is hard. Flotation chemistry is hard. It is not easily classified into neat pigeonholes that tell you of what can happen if you do X, Y, Z. Everything is nonlinear. Everything reacts with everything else. And there are multiple knock-on effects from every single little thing that you change. It is also, for that reason, seen as a very specialized area with an over-reluctance of so-called experts. And so-called experts can be people like myself who come out of universities who tell you that they know everything, or people like reagent providers who come out of their reagent shops and tell you that they know everything. In addition, plant trials, which is how you really tell how a reagent works in your system, are horribly expensive. They take up a lot of money, they take up a lot of people resources. They can be very difficult to design and even harder to execute. And they can also pose a very strong risk to your production schedule, because if you put in the wrong reagent and suddenly everything is going crazy, then your monthly production is going to take a big hit and you're going to have to explain yourself to your boss. In addition, the outcomes of plant trials are often very inconsistent. As I said, they are very hard to operate, and it is a very highly variable system where a great number of things are constantly changing when you have no control over them. For that matter, even if your plant trial is very well resourced, designed, and executed, there is still a good chance that you are not going to get the answer that you want, or even an answer that tells you clearly what the outcome of the trial was, because these are very complex systems that we are dealing with. And finally, flotation chemistry, oopsie, skipping ahead, is a bit of a dark art, okay? It is something that is seen as you have your flotation back, which is a big witch's cauldron, and you throw an iron-mutant turf from, and on the other side comes fully liberated chalcopyrite. I must also warn you that when I put this webinar together, this was at the start of the year when I was in lockdown with my young children, which explains the flavor of what you're going to see today. Please don't think too badly of me as a result. So how do we get here? How do we get to a point where flotation chemistry is seen more of a dark art than anything else? Well, it all starts with how we learn about it. It all starts with education at an undergraduate level. So in general, undergraduate programs in mineral processing have seen declines in student numbers over a great many years, pretty much all around the world, again with a few notable exceptions such as South America. As a result of dropping student numbers, the mineral processing curricula at universities have been progressively shrinking until the point where they become incorporated with a bigger and more prosperous chemical engineering undergraduate programs. Within those undergraduate programs, they are not seen as core subjects and are often relegated to elective status compared to something like petrochemical processing or catalysis, which are often in the chemical engineering curriculum seen as a much more core material. Because these courses are elective, there's very few of them, and you're forced with covering an absolutely enormous amount of information in a very condensed time. And as a result, a few of the more specific disciplines simply don't get covered, or get covered in a very, very narrow way that doesn't go into any level of detail. So as a result, flotation chemistry in particular is often taught by either someone who is an extremely well-versed mineral processing expert that isn't necessarily specialist in flotation chemistry, so say they know all about flotation hydrodynamics or all about comminution, but one person cannot know everything about such a wide field. And flotation chemistry is often one of the subjects that is dropped off by the wayside. Contrary to that, what can happen is that flotation chemistry is taught by either a chemist or a surface scientist. Now, these guys have an incredibly deep level of knowledge and a really, really solid understanding of all the fundamentals of chemistry and surface science, but they tend to have a very limited exposure to industrial flotation and the kind of situations that an average metallurgist will encounter on their daily basis and the kind of challenges that they face. So what does that end up looking like? It ends up looking like this, is that when we talked about reagents and undergraduate curricula, we get a very oversimplified view of what is happening. We are taught that there are different reagents, so collectors, depressants, frothers, and they have structures. So they have heads and they have tails, and they're made up of different building blocks. And they are given with a very reductive and simplified explanation. So collectors are hydrophobic. Depressants are hydrophilic. And what you see are diagrams that look something like this. Please mute your microphones. So you have particles, reagent molecules, and they look very cartoonish and they don't really explain much. And so what happens is we don't actually know what this means. So what makes a collector hydrophobic? What makes a depressant hydrophilic? Why are some collectors weak and others are strong? Why are some of them selective and why others are not? Why do collectors have frothing properties? Why do frothers have collecting properties? Why are molecules? You know, we don't know, and we're left grappling for an answer. I certainly had no idea what any of the answers to these questions were when I was a young metallurgist going forth into my first plant. So that's reagent chemistry. What about interfacial phenomena? Well, interfacial phenomena is often taught in a way that is overly complicated. So the subject of interfacial science often gets completely buried in the detail, where you have all the Hamilton constants and Gibbs free energies and DLVO theories and complex equations. Where often people see this material being taught in undergraduate, decide that this is too hard, and because it's too hard, it's no longer relevant, and they simply switch off. So as a result, this is taught to an inconsistent depth with a time frame that is too short to truly explain what any of it means. And in addition, this subject matter is very seldom placed within the appropriate context of mineral processing, where it is explained how this can actually actively benefit you and when you're trying to operate a flotation plant. So that's an undergraduate. What happens on site? Well, as most of you well know, that metallurgists learn on the job. The knowledge that they acquire is either passed down from senior staff if you're lucky and you get good ones. If you're unlucky, you don't get good ones, you're pretty stuffed. And then you always have the option of going with the handbooks. And the best and the most beloved example of that is Barry Wills's Mineral Processing Technology, a really wonderful really wonderful book that has seen a number of young metallurgists through their first few years on site, and it certainly has done me a lot of good over the years, and it's a really great publication. However, books like Barry Wills's book, as well as many people whom you speak to on site to help you learn about the process, tend to take a recipe approach. So if you want to achieve A, you add B. This knowledge and know-how is often very limited to specific sites. So you have people who have been working on that particular site for decades, and their knowledge about it is encyclopedic, so that they can tell you exactly what will happen if you tweak this knob or that knob. But the focus is always on the what, and it very seldom is on the why or the how. And then invariably what always happens is that your ore changes and your recipe simply no longer works. And then what? And so the result of all of this is that these are highly complex concepts that are really not well taught or not taught at all in undergraduate curricula. And when you get to site, your resources for learning about them are fairly limited and are often confined to a specific site. Now, while there is a great amount of literature that is available on flotation chemistry out in the scientific literature, it is generally aimed at chemists and surface scientists as well as researchers. And it is often written in a way that is completely inaccessible to practitioners. The relevance to flotation practice within these publications is often not made very clear, and the devil is lost in the detail. So as a result, many of these concepts are quite simply ignored. We decide that since we cannot make sense of them, we cannot apply them, so we don't need them. And so we simply pretend that they're not there. And so what happens is that most metallurgists of reagents can be boiled down to something like this. You have a list of ingredients that you mix together. You have sugar, spice, all things nice, and of course, chemical X. And for anybody who knows anything about flotation, X means xanthate. So you mix them all together, you stir them up and add some bubbles, and what you get? You get the Powerpuff Girls. And those are not necessarily going to equate to getting good, fully liberated chocolate pyrite out of your flotation cell. So while this is all meant to be a bit funny, the reality isn't actually that funny at all, because a great amount of productivity and possible process yield simply doesn't eventuate because we do not have a proper understanding of the underlying principles behind flotation chemistry. So if flotation chemistry isn't well taught in undergrad, how should we do it? There's no point poo-pooing the undergraduate system if we're not going to propose a viable alternative. So this is what I propose, how we do this. Let's get one thing perfectly straight. First and foremost is that there is no recipe. There simply isn't. There is no magic ingredient that you can find in a catalog that will only absorb onto chalcopyrite and leave pyrite alone, or absorb onto galena and leave sphalerite alone. There is no secret index that you get from a reagent supplier if you slip them a $100 bill under the table. That will tell you which molecule is specific to which mineral. Total chemical selectivity is a myth. It does not exist. Everything interacts with everything in a flotation system. But if you understand how a system works and why a system works, you can figure out ways to make it work within your specific flotation system in such a way that benefits you. So, how do we get to the understanding of the highs and the whys? In my personal opinion, there are 4 major components to understanding flotation chemistry. 1, understanding how surfaces work. 2, understanding what reagents are made of in a way that goes beyond heads and tails and little cartoony diagrams. 3, you have to understand what happens on a mineral surface and how that mineral surface interacts with the reagent, which you also know how it is built and how it is structured and how it works. And 4, you have to be able to put it all together within a practical flotation context. In other words, in a view of a practitioner, not in a view of a researcher or a chemist. So let's break those down a bit more. 1, let's start with surface forces. Flotation is all about surfaces. Surfaces of bubbles, which represent the gas-liquid interface. Surfaces of particles, which introduce solid-liquid interface. Particle bubble aggregates, which is a 3-phase solid, gas, and liquid interface. Surfaces behave very differently when they're immersed in water compared to that of air. They become impacted by a series of forces, which are attractive and repulsive. And a particle and a bubble are held together by a net attractive force. In other words, you have a balance between the attractive and the repulsive. So surface forces are a useful tool. They are not just something that you have to swat for an exam with big complex equations. Flotation depends on particles attaching to bubbles, and those things are held together by forces. Those forces can be manipulated using collectors, depressants, surface modifiers, and solution modifiers. Even in cases where you do not have full control of your surface forces, because sometimes you won't, if you understand how they work, it can help you understand the limitations of your system so that you do not spend millions of dollars and hours of effort banging your head against the wall trying to achieve the unachievable. And so whenever we talk about surface forces, I say keep calm and use the force. Trust me, you won't regret it. Second is we need to learn about the composition of reagents. And main flotation reagents, particularly collectors, prophets, and depressants, are actually a lot like Lego blocks. And like Lego blocks, they are made up of small building blocks that can be arranged in a myriad of different ways. And so what you have is actually quite a small number of basic building units that can be arranged in literally an infinite number of permutations. Which is why if you look at any flotation catalog, you will see rows and rows and rows and pages of different reagents that all look similar but not quite the same to one another. And so the way that I like to think about reagent building blocks is splitting them up into 2 groups. You have an absorbing group and you have a water-facing group. So an absorbing group is a chemical component that interacts directly with the mineral surface, either through a chemical interaction or opposite charge interaction or hydrophobic interaction, or there's actually quite a few interaction modes out there. And that group is what determines selectivity. You will notice that up here, I've got a block that says absorbing group, and in there I've got carboxylic acid, sulfonate, amine, and xanthate. Now, some of you would think, xanthate, that's a collector. Well, no, a xanthate is not a collector make because a xanthate is part of an absorbing group of a molecule. It is perfectly possible, and in fact, I have seen these things before, to have a depressant with a xanthate absorbing group. because what makes a molecule either a depressant or a collector is its water-facing group. And that is what determines the type of reagent. If it's water-soluble and highly water-interacting, it impacts hydrophilicity. In other words, it's a depressant. And an example of a long water-soluble molecule is a polysaccharide, the kind that you see in your carboxymethylcellulose type depressants. If the water-facing group is water-insoluble, like a hydrocarbon, it impacts hydrophobicity. Hydrocarbons are literally oils. They do not interact with water. They're completely water insoluble. And so what they do is they impact hydrophobicity onto a molecule and a surface which they coat. And the nature of this water-facing group is what determines the strength of that reagent. In other words, how long is the hydrocarbon chain? How many branches does it have? If it's a hydrophilic chain, again, how long is that chain? What are the other substitutions that are taking place within that chain? All of those things are fairly easily identifiable. And if you have a basic understanding of how it all fits together. These things essentially form a coating on top of mineral surfaces. You can think of the absorbing group as the glue and the water-facing group as the tile. So one holds the floor and the tile together, and the other one gives you a nice finish at the top. So understanding reagents is a useful tool. It's not just sticks and molecules. If you understand the basic reagent makeup, it removes all the mystery of chemical X, and it allows you to make informed choices when you are trying to select reagents that are particular to your process. It also allows you to interrogate your system when things go wrong. You'll be able to say, right, this didn't work. What were the components of my system? What doesn't match? It also reduces blind reliance on reagent providers who understand your particular plant and your system far less than you do. This is not to bag reagent providers. They are extremely useful and essential partners that you have to work with in order to make an adequate reagent selection. And understanding how a reagent works really allows you to improve that relationship and interact with them at an elevated level. So with that in mind, a note to talking to reagent suppliers. When you are speaking to a person who is on the face of it interacting with a mineral plant, you are speaking with either a sales agent or a former metallurgist, and often not a chemist, sometimes a chemist, but often not. And so they may not be the correct person to be asking very pertinent questions regarding the makeup of the reagents because they may not know the answer. But if you are asking them the right questions, they will be able to point you to somebody within the organization who will be able to answer those questions. And they are sometimes based in Sweden and you have to call them at an ungodly hour to get them to pick up the phone, but that's just life. Also, reagent companies do not like to reveal the compositions of their products. The main reason for this is commercial sensitivity. There is a highly competitive business where a number of companies are competing with each other in a market that is really quite cutthroat. And for that reason, they really don't like to talk about the nature of their products to avoid copying and copyright infringement or IP infringement. But the second reason is, as I said, you are speaking to someone who's a sales agent or a metallurgist. They often themselves do not have the necessary depth of knowledge and understanding of their product, but they will be able to point you to somebody who does if you ask them the right questions. Next is that products are not a single pure product. They are a mixture of several reagents. And it sometimes can be hard to know which component does what. And so a really good tip is to request an SDS from your reagent provider, where you can look up and see exactly which chemical components are contained within. If your reagent provider tells you, gives you an MSDS that says it contains substances, find a new reagent provider. So ultimately, being informed and understanding the underlying basics can really help you find a common language with your reagent provider, help ask the right questions, and really get the most out of that really essential relationship. 3, we have to understand mineral surface. Flotation is all about surfaces. And different minerals will have very different chemical compositions, which means that they will also have a different surface chemistry. And that surface chemistry determines how a reagent will interact with that surface and what properties will be impacted onto that surface as a function of reagent interactions. A really great set of developments in the modern scientific state of the art has been that we now have access to fantastic equipment that gives us surface-specific analysis of minerals, and not just on pure mineral surfaces, but on complex composite particles directly out of a mineral stream. So over here, I have some examples of what TOF-SIMS or macroprobe analysis looks like, in this case on pure talc or pure pyrite. But this here in particular is a TOF-SIMS analysis of a composite chalcopyrite particle within a real-life process stream taken as a sample, and that allows us to make several levels of analyses about how those particles are interacting with each other, but also within reagents in the system. It's a very, very powerful tool, and we now have access to tools like this, whereas we did not, say, 15 years ago. So the next thing is that you really have to understand your ore. You cannot come up with an appropriate suite of reagents and choose what is right for your ore if you don't understand its components. It sounds really simple, but you'd be amazed how often this simply doesn't get taken into consideration. So when you're dealing with your ore body, get an MLA analysis. Get it as a function of particle size for both your feed, your concentrate, and your tails. This will help you analyze the key minerals, figure out, are they valuable? Is there more than one valuable species? Do we need to recover them separately, or is one bulk concentrate okay? Are any of them deleterious? Do you just have to reject them from your concentrate, or are they actually toxic and you have to sequester them in a separate stream and get them disposed of in a separate manner? Is your gangue floatable? If it is floatable, how badly? All of these are important questions to ask to figure out what is it that you are getting reagents for? What is it that you want them to do? And you cannot figure that out until you thoroughly analyze your ore. So get those MLAs done. And so understanding your ore is a useful tool. There's a bit of repetition here. Understanding key components of your ore is vital to reagent selection. And minerals and their compositions can be quite easily looked up either in literature or using reputable internet sites as mendat.org. This will give you a very broad overview, but it's definitely a starting point, because the nature of a mineral surface will determine how that surface can be manipulated, whether with a surface that needs to be made hydrophobic or hydrophilic, or whether it's a sulfide surface or an oxide surface or a carbonate surface, etc. And the one resource that most people simply fail to tap into is that every site has a geology team. But for some reason, the geologists and the metallurgists just don't talk to one another. Either they don't understand what each other is saying, or they just had a falling out 10 years ago, and ever since the twain shall never meet. It's like the Capulets and the Montagues. Make friends with your local geologists. Take them out for beers. Talk about rocks. They love that stuff. And you will not regret it. It'll be one of the most valuable investments of your time that you can ever do. Make friends with a geologist. And the final step, that is arguably the most important of all, is putting it all together. Any kind of information is always best cemented by demonstrating how it is useful to your everyday experience, in this case, as a flotation practitioner. And the best way to do that is by looking at a number of case studies. You look at laboratory trials, you look at plant trials and full-scale trials, and you learn what you can learn within either your own system or a system that is very similar to yours. For that reason, it's always very helpful to have lots of friends in the industry that will let you use this site data to analyze it and learn from it. Those are rare, and when you find one, you hold on to them and never let go. So then, once you have put everything together, you have gathered all the system information that you can to help you interpret the results of your own site performance, minerals and their mineral surfaces, reagents and their components, the effect of all of these on interfacial forces, you can start to analyze the performance of your own plant. And you should always do so in the most systematic manner possible. In other words, always ask yourself, what do I expect to happen before trying something new? And then once it's happened, did what I expect happen, or did something else happen? What was the difference between reality and expectation? What caused it? And how do we fix it? Because once you have all of that information neatly lined up, that answer becomes a lot easier to come by. So to summarize, flotation is hard. It really is, make no mistake. But it is also quite badly taught at undergraduate level. It doesn't need to be this way. Flotation chemistry can be taught. It can be explained, and that knowledge can be transferred in a way that discards the very reductive approach of a recipe. It has to cover the underlying basics, explaining the hows and the whys of not just reagents, but also your ore. And it has to put it into context of real-world flotation practice. We do not do this so we can pass exams. We do this so we can operate flotation plants, and the two are very different. So how do we do this right? Well, I've spent a long time thinking about this, and this is the approach that I take when teaching flotation chemistry. One is cover your underlying principles. We've talked about this quite a lot. Talk about how surfaces work, how reagents work and what they're made of, what happens on mineral surfaces, and how do you put it all together in a practical flotation context. Two, always respect your audience. Metallurgists know their stuff, they know their plants, they have an absolutely incalculable breadth of experience when it comes to their sites, and they know their site far better than any researcher like me or a reagent manufacturer. Always, always be prepared to learn as much from your audience as they learn from you. It's an interaction, not a one-way knowledge transfer like a webinar. Always put your material into context that is specifically relevant to your audience. Three, select the right people to prepare the course material. With this, it's extremely hard to find any one person that has all the correct expertise to cover all aspects of the material. And so you don't need one person, get a team together. Make sure that you have the right people in the room that can address any particulars of a new big system. And it's always useful to include a chemist or a surface scientist. Four, my biggest favorite is no talking and talking. The audiences need to be engaged with on this, which is why presenting material as pre-recorded online, I find, is a very poor way of presenting material that's complex, particularly within a condensed amount of time. One needs to be prepared to answer any and all questions, and you'll all get your chance to grill me shortly in the Q&A section. And one must always bring the material back into the context that is specifically relevant to your audience. But, very big but, when you have a big hammer, all problems start to look like a nail. So it is very important to beware of tunnel vision and keep an eye on the big picture. Chemistry is a very important aspect of flotation, but it is but one out of many aspects of flotation systems. Others are ore liberation, particle size, cell design and hydrodynamics for different types of unit operations, circuit design, circuit configuration, and most importantly, your site operational practice and the skill and experience level of your metallurgical team. So from that point of view, your metallurgical team is a much greater investment than any single unit operation within your plant. And that metallurgical team really requires a lot of input and a lot of investment in terms of their development. And ta-da, here comes the product spruiking. JKTech offers a series of professional development courses to make you make the most out of your metallurgical team. They cover quite a wide range of expertise, ranging from comparative statistics down to value chain optimization and workshops, as well as offering these short advertising webinars to get you all interested. As well as SMI as a whole offers a much greater range of professional development courses, ranging from flotation chemistry, which is a course that I offer, through process mineralogy, geometallurgy, and social performance fundamentals. So I will urge all of you to please go onto the SMI and JKTech professional development websites and peruse the wonderful selection of courses and professional development opportunities that we have available. We love to have you, and one of the best parts of our job is to share what we know with everybody, but also learn from you in the process. And with that in mind, we have 15 minutes left. I am going to stop talking, and I will give everyone the opportunity to give me their questions in the chat sections.